In the last video, we saw that the derivative of a multivariable function is a linear function, and it's represented by a matrix, and that matrix is the matrix of partial derivatives called the Jacobian matrix. In this video, we will look at an example of applying this whole process. Okay, so I'd like to take one example and just to work this out and see if we can figure out what it means. So let's take the function from, I want something that we can visualize. So we're going to go from R2 to R. So this is something we can graph in 3D. It's a surface plot. And let's just do x plus y squared over 6 minus xy over 6. Okay, and that is just a random function. So let's see if we can find this this derivative. So we start off, well, first of all, what size is it going to be? Well, what do we have here? We have one component for our, we have one component for our result, and we have two components for our input. So we have to take two partial derivatives. We have to take a partial derivative with respect to x, and we have to take a partial derivative with respect to y, but we only have one function to do that with. So since the functions vary across the rows, down the rows, and the variables vary across the columns, we're going to have two columns. We're going to have two columns and one row. So it's going to be a 1 by 2 matrix. Okay, so let's fill it in. So let me I'll make it a little bit bigger. And I erase my function. Okay, so we're going to have a 1 by 2 matrix. So, like this. Okay, so the first one is going to be the partial of our function with respect to x, and the second one is going to be the partial of the function with respect to y. Right. And the way to take partial derivatives, hopefully you know this from your regular single variable calculus class, is just to keep all the others constant and take the derivative with respect to whichever variable you're looking at. And that may have seemed sort of like an arbitrary rule, but now I think in multi-dimensions this makes sense. Here's a picture of the graph, and a partial derivative is saying, okay, well what's the derivative in the x direction? Here's the x-axis right here. What's the derivative in that direction? Well, one way to think about it, or what's the rate of change in that direction? Well, if we freeze y and z, if we freeze y, or do the plane y equals 0, then, or y equals a constant, then we intersect this curve and we get a nice plane curve, which we can find derivative like normal. Okay, so. Alright, so, and I actually didn't specify what point we want to do this at. So we're going to do this, we'll do it when xy is equal to, say, 1, 1. It's nice and easy. So to find our Jacobian matrix, we got df partial with respect to x. So we keep, we let x vary, and we let the other ones constant. So derivative of this is just 1. The derivative of this guy, it's a constant, so it's 0. And the derivative of this is just, it's a constant times x. So a constant times x, the derivative of that is just the constant. So it's y over 6, or 1 y over 6. So we get 1 minus y over 6 is our first one. And then the second one, we hold x constant and let y vary. So again, x is just a constant. Derivative of the constant is 0. Derivative of this is 2y over 3. 2y over 6, which is just y over 3. And this is just y times a constant. Derivative of that is just a constant. So filling that in, we've got y over 3 minus x over 6. Okay, great. That's our Jacobian, which, like I said, is the derivative. Now, what does that mean? Or we want to do it at this point. So to find at a point, we plug in 1, 1, and we get 1 minus 1 over 6, comma, 1 over 3 minus 1 over 6. and 1 minus 1 over 6 is 5 6, and here we get 1 over 3 minus 1 6, that's 2 6 minus 1 6 is 1 6. Alright, great. So this is our matrix L, right? And L times x is our linear function, which is going to give us our approximation. So, I'm sorry, not L times x. Our linear function, L times xy, because the input for this is a 2 by 2. So let's try and graph this. Now, be careful. This is not the tangent linear function. This is just a linear function, and we'll see that in a second. So if I go back to my function, here's a graph of it. Okay, so the first thing I'm going to do is I'm going to plot the point that we want to do. So the point is just when x is 1 and y is 1 and z, it turns out, well, you get 1 plus 1/6 minus 1/6, so just 1. So 1, 1, 1. So if we look, that point is on our curve, and what we want to do is we want to find the derivative at that point. And okay, so what does that turn out to be? Well, we figured out that it was 5 6 comma 1 6. So if I take that and I do the matrix multiplication, I get 5 6 x plus 1 6 y. Okay, and if I graph that, I get a plane which appears to be tangent at that point. Our function to begin with happened to be a linear function, so that means that our linear function is going to be the actual tangent. Now, if I take my function and do just a simple translation, if I just shift it up 1, right, then my point, instead of being 1 1 1, becomes 1 1 2. Now, by symmetry and just from the laws of differentiation, we know that the tangent is going to be the same thing. But now this function, this plane that we had, is no longer tangent at that point, and that's that's not really a problem because it's just we just need to translate it. So if I took my derivative, I could easily translate it up. I just translate z. I translate z by subtracting 1 from it, and now I see that I have my tangent plane back. Right. So that's essentially the same idea as writing your tangent line in point-slope form, where the coefficients of x and y, or the coefficients, which essentially is our matrix, gives us the direction or the slope of the plane, and then we subtract. We do y minus y1 and x minus x1 to do to incorporate the point in which it goes through. So it's exactly analogous to point-slope form. All right. So in summary, the Jacobian matrix is the matrix of partial derivatives, and if you plug in x and y values at a specific point, that Jacobian matrix is going to give you the direction, the linear function, which sort of tells you the direction or of the function at that point, and the direction in all cases. In other words, it's the linear function which best approximates your original function at that point. And we can write an equation for a tangent line just by taking our Jacobian matrix, writing a linear function with it, and making sure that we translate all the coordinates to that point. Okay, that's it for this one. See you next time.